Hello everyone, my name is Gaganjeet Reen and today I will be presenting DPIFuzz, a differential fuzzing framework to detect DPI elusion strategies for QUIC. This is my joint work with Christian Rosso and was developed during my time at the CISPA Helmholtz Center for Information Security. Let's start with an overview of QUIC. QUIC is a transport protocol that has the potential to replace TCP in the near future. It is encrypted by default and is conceptually similar to a combination of TCP, TLS, and HTTP2 implemented on UDP. QUIC packets are carried in UDP packet payloads. A single UDP packet can include multiple QUIC packets. Each QUIC packet itself has a header and a payload. The payload is comprised of one or more frames in most cases. The QUIC payload and most fields of the QUIC header are encrypted. Each frame itself contains multiple frame-specific fields. Similar to HTTP2, QUIC has the concept of streams. A single QUIC connection can have multiple streams to facilitate the transfer of data. Now that we have an idea about QUIC, let's discuss the threat model that we consider for our paper. Assume a typical enterprise network with all the communication happening over QUIC. The devices inside the network need to communicate with the devices outside, and all the traffic passes through the QUIC monitoring system present at the edge of the enterprise network. The monitoring system consists of two components: an inline proxy for decrypting the encrypted QUIC communication, and a DPI system for inspecting the decrypted content. An attacker would want to bypass the DPI system and get sensitive data out of, or malicious data into the enterprise. Our primary goal is to enable organizations and DPI users to automatically detect potential strategies that could be used to bypass their stateful reassembly-based DPI systems. We aim to find such sequences of QUIC packets that contain payload that is deny-listed by the DPI system, which however remains unnoticed by the DPI system. Let us understand with an example what the solution could possibly look like. Assume that the DPI system has deny-listed the keyword ABC. An attacker sends a sequence of QUIC packets to the monitoring system. The DPI system reassembles the sequence to something other than ABC and lets the traffic pass through. The endpoint on receiving the traffic, however, reassembles the content to ABC. Thus, the attacker was able to evade the DPI system successfully. Using DPIFuzz, we automatically uncover such sequences which are reassembled differently by the DPI system and an end host and could potentially allow for DPI elusion. And we broadly do so in the following manner. We first use fuzzing to generate a sequence of packets. We use 5 popular open source implementations to model a DPI system. To model an inline proxy that forwards the packets to a DPI system for further inspection, we feed the same logical sequence of packets to the DPI system and the end host implementation, and then analyze the data reassembled by the implementations to check whether they interpret the data differently. Some of the challenges while designing a fuzzer for a protocol like QUIC were: implementations of protocols like QUIC expect packets with very specific structure and field values, in the absence of which the packets are discarded right away. A fuzzer will only be able to detect meaningful vulnerabilities if it can inject unexpected inputs deep into the state space of a protocol. To deal with this, we design a smart fuzzer which has structure-aware generators and mutators. Secondly, QUIC is an encrypted by default protocol, and fuzzing encrypted packets will almost certainly render a packet structurally invalid. To tackle this, we fuzz the packets before they're encrypted. And lastly, we cannot replay previously captured traffic because completing a handshake is essential before any data can be exchanged. Our fuzzer is capable of completing handshakes as well as interacting actively with the implementations. A fuzzer can broadly perform 2 types of mutations. We have packet-level mutations, which take effect on individual QUIC packets, and sequence-level mutations, which are defined for a sequence of QUIC packets as a whole. We further define 2 kinds of packet-level mutations. First, we have payload-level mutations, which consider the entire payload of QUIC packets as a single blob of bytes and perform mutations completely ignoring the structure of the payload and the frames within the payload. The second type of packet-level mutations are frame-level mutations, which are defined for individual frames in the QUIC payload and fuzz the values of the various fields in the frames. Given a sequence of packets, our fuzzer can shuffle the order of packets in the sequence, duplicate a random set of packets, or even drop a random number of packets from the sequence. Now that we know the mutations that a fuzzer can perform on an existing sequence of QUIC packets, let's discuss how these sequences are generated in the first place. We use packet generators to generate these sequences, and we define two kinds of packet level generators. First, we have randomized generators, which randomly decide which types of frames and packets to create and send. The user or the tester has no control over the sequences being generated. And secondly, we have controlled generators, which are used to create specific types of packet sequences that we want to test our implementations with. This allows us to focus more on specific aspects of an implementation that we want to test. We define three kinds of control generators for our use case of stream reassembly, the details of which are available in our paper. Considering DPIFuzz to be a black box, we provide three inputs: server addresses of the implementations we want to test, the list of generators that we wish to use to generate sequences, the number of times we wish to use each generator in the list to generate sequences for each implementation. And as output, we get a result file which contains the packet sequence details along with a list of implementations that exhibit diverging behavior for those sequences. Let's now understand the internal working of DPIFuzz. We consider 5 open source QUIC implementations and design echo servers which can return the data reassembled by these implementations. DPIFuzz first establishes a connection with each of the 5 implementations. Followed by this, sequences of QUIC packets are generated and passed through mutators. We use a deterministic random number generator to guide the randomized decisions taken in the generators and the mutators. This allows us to easily recreate sequences at a later point. These mutated packets are then encoded and encrypted and sent to the implementations. The responses from the implementations are received by the response analyzer, which then generates trace files for each response. Each trace file contains the application level payload returned by the implementations and a status code which indicates the state a server was in after processing a sequence of packets. Some of the examples of status codes are server alive, which indicates that the server was alive after processing a sequence of packets, or server not responding, which indicates that a server was in a non-responsive state. The trace files of all the implementations for a particular logical sequence of packets are compared, and then all the implementations that had differing behavior are recorded, along with the seed value and the generator used to generate the said sequence. We then replay the sequences again later and analyze the cause for the divergent behavior of the implementations. The experiments were run on a machine with a quad-core Intel i5 processor with a 16 GB RAM running Ubuntu 18.04. To remove the effects of network latency and unintentional packet reordering, we run our echo servers as well as DPIFuzz locally. In total, we use a framework to create 600 unique sequences. That is, we run our fuzzer against each of the 5 implementations with each of the 3 specified control generators with 200 different seed values. We also ensure that the echo servers are configured with the same transport parameter values. The first way to elude DPI systems uncovered by DPIFuzz is based on the idea of inserting packets with duplicate packet numbers that are ignored by some implementations but not by others. We can see in the table that the keys server reassembles more data as compared to the movefast and the quickly server. The reason is that after receiving packets containing stream frames of one stream, servers receive a packet with a duplicate packet number. This packet has undergone a payload level mutation at the fuzzer side, because of which the frames in the payload are structurally invalid. While the keys server is configured to drop the packets with the duplicate packet number, the other 2 servers attempt to process the packet, which results in a frame format error and the connection is closed. Any data sent after this is not reassembled by the servers. Another way to elude DPI systems discovered by DPIFuzz is based on the idea that implementations might handle receiving data at overlapping offsets in different ways. Looking at packets 3, 7, and 8 in the table, we can see that when the keys server receives a payload at an offset that it already has data for, it simply ignores the new data. The quickly server, on the other hand, replaces the payload with a new payload that it receives. The movefast server only replaces the existing data if the starting offset at which the payload in a stream frame starts is unoccupied in the stream being reassembled. We now demonstrate with a simple example how we can elude a DPI system using these results. Assume that a DPI server has deny-listed the keyword blocked. Consider a DPI system based on the quickly implementation and a destination server based on quiche. We send a stream frame containing the payload OCKED starting at offset 2 to the implementations, followed by a frame containing the payload BLIN starting at offset 0. Please note the offsets are 0 indexed. Characters at offsets 2 and 3 overlap, and while the DPI system reassembled the stream as blinked, the destination server reassembles the keyword blocked. Similarly, we can elude a DPI system based on quickly when the destination server is based on move fast. In addition to the reassembly-based differences, we also uncover 4 security-critical vulnerabilities in the tested QUIC implementations. The move fast server tries to dereference a null pointer, which causes the server to run into a segmentation fault. This happens because the implementation is unable to handle a specific kind of packet with contradictory field values. The quant server runs into a heap use after free error because it tries to check whether a stream is closed or not after the memory allocated to the stream has already been freed. The quickly server runs into a segmentation fault when the server receives a stream frame from a client with the stream ID not permitted by the QUIC specification and tries to access the value stored in the null pointer. The Neko server runs into an assertion failed error because the Neko server tries to close an already closed connection. To summarize, we first discussed the threat model in which attackers attempt to bypass QUIC monitoring systems in enterprise networks. We explained how sequences which are reassembled differently by the DPI systems and the destination server can be used to potentially elude a DPI system. We then proposed DPIFuzz, which leverages differential fuzzing to identify sequences which are reassembled differently by the QUIC implementations, and in the process also uncovers 4 security-critical vulnerabilities in the implementations. The code for DPIFuzz is open source and can be easily used or extended by organizations and DPI users to test the robustness of their DPI systems and identify potential shortcomings in their methodology. Thank you for your time, and I would be happy to address any additional queries.